All right, in this video, I want to talk about section 6.6. And here what we're going to do is we're going to talk about the inverse trigonometric functions. So here are the inverse trig functions. So I want to introduce what these functions are. There's a few kind of domain and range things to talk about. We'll graph a few and then we'll talk calculus, okay, with these functions. So the first thing is if we were to take the function y equals sine of x and graph it, we know what this looks like. Okay, so this is a picture you've been drawing for however long. So it looks like that and continues indefinitely, and it looks like that and goes in both directions. Okay, and the problem is that that function is not one-to-one. Okay, if it does not pass the horizontal line test, you're not going to get an inverse. What we have to do is we have to restrict the domain, much like we did in previous sections. And so we're going to restrict the domain from here to here. Okay, so that's from negative pi over 2 to pi over 2. Okay, and so we'll erase the rest. And then we'll erase over here. And then that's the part of sine that we care about. Okay, that's a pretty bad drawing of sine, but it should probably look something like that. Whatever, you know what sine looks like. So that's the sine function. So we're thinking about sine of x, specifically with the domain being from negative pi over 2 to pi over 2. And then the range from negative 1 to 1. Okay, and so that's the function that we can find the inverse to. And the inverse, we're going to write it in one of two ways. There's two customary ways to write it. One is arcsine. Okay, so arcsine is just the inverse function of sine of x. And here, this function is going to look like this. So arcsine, let me organize this just a little better. Arcsine is going to look exactly like this picture over here, except reflected about. So the way I like to think about this is you take your paper and then you flip it 90 degrees like that. So you take it and then you flip it like that. And so it's going to have a domain from negative 1 to 1, including both of these, and the range from negative pi over 2 to pi over 2. Okay, so it's going to go from negative 1 to 1 and negative pi over 2 to pi over 2. And it's going to look something like, that. Okay, so it's going to be concave down from negative 1 to 0, and then concave up from 0 to 1. Okay, and that's arcsine. And so the defining feature here is that before I go on and say one other way to write this, sometimes it's nice to write arcsine because it's clear what we mean. But instead of writing arcsine of x, sometimes it's also customary to write sine inverse of x. And that inverse reminds us that this is the inverse sine function. The problem with that notation is that when you write sine squared, that means sine of x squared. But with this notation, the inverse sine, this is a new function. It does not mean sine of x to the negative 1. Okay, so just be careful. That's really the big reason, this kind of ambiguity here is the big reason why people use the arcsine definition or terminology. Okay, so arcsine is the inverse sine function with the specific domain and range. So that's that. What this means is that if you were to want to find, say, if you were to want to evaluate, let's do it this way. Let's find arcsine of 1/2. Okay, so let's figure out what arcsine of 1/2 is. Let's call it theta. It's going to be some angle. Now, arcsine of 1/2 being theta is equivalent to saying that sine of theta equals 1/2. This is very much like when you have f inverse of say some value 2 being equal to t, that's the same as saying f of t equals 2. We're doing exactly that thing, just with arcsine, and sine is our original function. So arcsine is our inverse, sine is the original. So arcsine of 1/2 is going to be theta if and only if sine of theta is 1/2. And then we need to think about what's the angle theta that we can plug into sine to get 1/2. And it turns out that that's going to be pi over 6 if we restrict to this range, right? We would actually have infinitely many values if we didn't restrict our domain, but we restricted our domain to be from negative pi over 2 to pi over 2. Okay, so that's arcsine. Arc cosine works the same way, but it turns out that as far as the calculus part goes, knowing just arcsine is enough. You don't need arc cosine. There is also arctangent. So here the stories are very similar. For tangent of x, I'm just going to do the details one more time with tangent. So with tangent of x, the graph is going to look like this. And we know that tangent is pi periodic. It's defined from negative pi over 2 to pi over 2. And it has asymptotes. I'm going to draw them in red. It has asymptotes at pi over 2 and negative pi over 2. And it's going to look something like that. Okay, so this is tangent of x. And then it also repeats, except we're going to get rid of the terms that repeat. Okay, so that we have a one-to-one function so that it passes the horizontal line test again. Okay, so that's tangent of x. So here our domain is going to be from negative pi over 2 to pi over 2, not including the endpoints. And our range is going to be from negative infinity to infinity. So all real numbers. And so that means that the inverse function, so y equals tan inverse of x, or if you like, if you prefer the arc tangent of x, that's fine. Many people use both notations, so I'm going to try and use both notations as well. But this function is going to look like this. So it's, first of all, its domain is going to be all real numbers. Its range is going to be from negative pi over 2 to pi over 2. And again, flip it about the line y equals x. So flip the page front to back and then rotate. And what it's going to look like is we're going to have asymptotes at pi over 2 and negative pi over 2. Those are horizontal asymptotes, and it's going to look something like this. Okay, so it's going to go through the origin, and then it levels off at pi over 2 and negative pi over 2. So as x goes to infinity, inverse tangent of x goes to pi over 2, and as x goes to negative infinity, inverse tangent approaches negative pi over 2. Okay, so I think I said that correctly. As x goes to infinity, inverse tangent goes to pi over 2. As x goes to negative infinity, the function goes to negative pi over 2. Okay. And then we're going to do something similar with secant. I'm not going to worry too much about the domain and range of secant. Okay, but we have y equals secant of x. And then I don't care too much about the graph of secant. We'll just kind of see how calculus plays with each of these. The graphs of sine and tangent are much more important. So with that being said, let's evaluate derivatives. So what I want to do is I want to evaluate what's the derivative of inverse sine. Okay, and so we're going to figure out what that is. And the way that I want to evaluate this derivative is, let's write y equals inverse sine of x. And I want to calculate its derivative. And the way that we'll do that is to actually rewrite this equation as sine of y equals x. We can take sine of both sides because it's 1-to-1 and we have an inverse function, so that's fine. And then we know how to differentiate sine. This becomes cosine of y times y prime is equal to 1 because we're differentiating both sides with respect to x. So the derivative of sine of a function is going to be cosine of that function times the derivative of the inside. The derivative of x is just 1. And then this tells us that y prime, the derivative of inverse sine, in other words, is going to be 1 over cosine of y. And we have two problems. The first is that I don't want to write a derivative in terms of the function itself. That's a differential equation, and that's not so helpful for figuring out what the derivative is going to be. And also, I don't know what cosine of y is. I know what sine of y is, but not cosine. And we can solve both of those problems actually using the same method here. We know that sine of y plus cosine of y, if we square them both, so sine squared of y plus cosine squared of y is equal to 1. So that's the first thing that we know. Okay, so sine squared plus cosine squared is 1. We also know we can arrange this. So cosine squared of y is 1 minus sine squared. And then also, if you think about the domain that we're allowed here, this means specifically when we talk about the x values of sine being between negative pi over 2 and pi over 2, that's exactly where cosine is positive. And so we can actually take square roots of both sides and everything is fine, because specifically over the values where inverse sine is defined, that's exactly where cosine is positive. So if you restrict from negative pi over 2 to pi over 2, cosine is positive there. We can just take square roots and everything's fine. So it turns out that cosine of y is the square root of 1 minus sine of y quantity squared, and sine of y was x. So it turns out that cosine of y is equal to the square root of 1 minus x squared. And therefore, the derivative is going to be 1 over the square root of 1 minus x squared. Okay, so in summary, what we just showed is that if we differentiate inverse sine of x, we get 1 over the square root of 1 minus x squared. Okay, that's the first of the 3 inverse trig functions that we need to know how to differentiate. The next is going to be tangent. So we're going to play this game again and again with tangent and secant. And those are going to be the 3 inverse trig functions that we'll need for our study in Calc 2. So next, let's look at inverse tangent. So we want to evaluate the derivative of inverse tangent, or arctangent, if you want to write arctangent. And so what I want to do is I'm going to write y equals, so same method as before, y equals inverse tangent of x. And we can take, because we restricted the domain in a way that makes this function 1-to-1, we can talk about an inverse, and we can take tangent of both sides. So this is equivalent to saying that tangent of y equals x. And now we can differentiate, again, implicitly using the chain rule. We end up with secant squared of y times y prime is equal to the derivative of x, which is 1. And now again, same problem as before. How do we write secant squared in terms of tangent? And we need to know a trig formula with secant squared and tangent squared in it. And it turns out I am terrible at remembering things, but I know that there's certain things I don't have to, and this formula is one of them. We know that sine squared plus cosine squared is 1. And we want to get from this a formula involving tangent squared and secant squared. So what I'm going to do is I'm going to divide both sides by cosine squared. And what we get is tangent squared, right? Because we have sine squared over cosine squared, plus cosine squared over cosine squared, so plus 1, is equal to 1 over cosine squared, or secant squared. So that's how that formula shakes out in terms of tangent and secant. And therefore, secant squared is going to be, so our derivative is going to be y prime is 1 over secant squared of y. Secant squared of y is just 1 over, let me say that. Secant squared of y is 1 plus tangent squared. So our derivative is 1 over 1 plus tangent squared. And then finally, we said tangent of y was x. So this is 1 over 1 plus x squared. So altogether, this means that the derivative of inverse tangent is 1 over 1 plus x squared. Okay, so again, that's the second big result for the section. And then the last one is inverse secant. Okay, so same games, same story. Let's let y be inverse secant of x. This tells us that secant of y is equal to x. And then we can implicitly differentiate both sides so that secant of y times tangent of y times y prime is equal to 1 after we differentiate both sides. And then we'll get y prime on one side, everything else on the other. So y prime is going to be 1 over secant of y times tangent of y. And secant of y is x. So now we only have to worry about tangent of y. And if we go back up to our equation, tangent of y, let me recopy it here. So we know that tangent squared plus 1 is equal to secant squared. And so this tells you that tangent is going to be the square root of secant squared minus 1. Again, I didn't go over the details here, but the restriction of inverse secant, the domain that we chose, is exactly where tangent is positive. And so we can take square roots, everything's fine. Okay, and so tangent of y is the square root of secant squared minus 1. And so altogether, so this is 1 over secant of y times the square root of secant squared y, so secant of y all squared minus 1. And so if I write that in terms of x, that's 1 over x times the square root of x squared minus 1. And these are just 3 derivatives that we need to memorize. And so they're so important, I'm going to write them again. So the derivative of inverse sine, or arcsine if you prefer, is 1 over the square root of 1 minus x squared. The derivative of inverse tangent is 1 over 1 plus x squared. And the derivative of inverse secant is going to be 1 over x times the square root of x squared minus 1. Okay, and so those are the 3 big derivatives to know. So now what we can do is we can differentiate and anti-differentiate if we like. And so let's see, we can do a few things here. Let's evaluate the following. So I just want to do just some very simple, straightforward problems, and then we'll do more complicated problems on the worksheet together in class next week. So, or maybe this week, I guess it depends when you're watching the video. So we're going to evaluate the derivative. So evaluate f prime if f of x is inverse sine of e to the x. And so what I want to do actually before I do this is I'm realizing I forgot to write down how these functions interact with the chain rule. And so this is not going to be surprising, but it's worthwhile me writing this down anyways. Okay, so let's put a little line here. If I were to have inverse sine of a function u, so remember u is some function of x. If you don't like using u, you can use g of x. And then we're going to differentiate. What I'm going to get for the derivative is going to be the same thing that we got before. So it's 1 over the square root of 1 minus u squared times the derivative of the inside. The derivative of inverse tangent of u is 1 over 1 plus u squared times the derivative of the inside. The derivative of inverse secant of u is 1 over u times the square root of u squared minus 1 times the derivative of the inside. And as much as I hate memorizing, you just have to memorize these. There's no way around that. Do not try and figure out these derivatives on the fly. It just takes too long. It takes a couple minutes each time, and you just won't get anywhere on the tests, right, that are timed. So we just have to sit down and we just have to memorize these. There's really no way around that. Okay, it's just like all the other derivatives. Once you have them memorized, then you can just use them fluidly and everything's fine. Okay, so let's start with evaluating f prime if f of x is inverse sine of e to the x. And so our derivative is going to be, well, if we follow the pattern for inverse sine, we're going to have 1 over the square root of 1 minus our argument, in this case e to the x, squared, times the derivative of e to the x. Okay, and so that's, if you want to just write it all in one step, 1 over the square root of 1 minus e to the 2x times e to the x. And if you want, you could even put the e to the x in the numerator. It's fine. Okay. What if we wanted to evaluate the derivative if f is equal to the natural log of inverse tangent of x? Remember, inverse tangent of x is not an exponent. That -1 means that it's the inverse function. It is not an exponent. Okay, so just be careful there. So the derivative here would be 1 over the inside, so 1 over inverse tangent of x, times the derivative of the inside, which in our case is 1 over 1 plus x squared. And again, inverse tangent of x is not tangent of x to the -1. So there's no algebra simplifying you can do here. Okay, this is it. This is as simplified as it gets. Okay, so that's that. Let's evaluate. Let's say I wanted to evaluate the antiderivative of, let's do it this way. Let's do x over 1 plus x to the 4th. Okay, and let's think about how could we differentiate this? Ignoring the x in the numerator for a second, this looks a lot like an inverse tangent function, which just at first glance seems okay because you have 1 plus something. Here it's to the 4th. But if we wanted to write this as something a little bit more recognizable, we could write this as the integral of x over 1 plus x squared. And now hopefully you can see where this is going. So now we can substitute u equals x squared. Du is going to be a constant multiple of x dx. So we can move the constant over. And here we have our x dx. So that's that. We're going to have a 1 plus u squared in the denominator. And then I forgot the 1/2 out front. So we get 1/2 times the integral of 1 over 1 plus u squared du. Okay, and so when we do that, we're going to end up with, this will be 1/2 inverse tangent of u plus c, which is 1/2 inverse tangent of x squared plus c. Okay, this was a badly written u. Okay, and so that's how we evaluate the derivative there. If we were to evaluate, say, the integral of 4 over 9 minus x squared. Okay, let's think about how we would evaluate that integral. And that integral, what we're going to do is we're going to first notice that this looks a lot like an inverse sine function because you have a constant. I mean, this 4 can move outside. I don't care. The only annoying thing is that if this was a 1, this would be inverse sine. And so what we're going to do is we're going to make it a 1. And what I mean by that is we're going to factor out a 9 from underneath, from inside the square root. So we're going to factor out a 9. We'll be left with 1 minus x squared over 9. And then what we can do is we can bring the constants outside the integral. So we can bring out the 4. We can bring out the square root of 9. So altogether, that'll be 4/3 times the integral of 1 over 1 minus x squared over 9. And if you like, even at this point, we can write x squared over 9 as x over 3 squared. And that hints to us that we should substitute u equals x over 3. Because then du will be 1/3 dx, so that 3 du is equal to dx. And then plugging back in, we're going to end up with, so we have this 4/3 out front. We're going to have the integral of 1 over square root of 1 minus u squared du. And then the dx was actually 3 du, so I need another 3 out front. Okay, so altogether, this will be 4/3 times 3, which is 4. And then the antiderivative of 1 over square root of 1 minus u squared du is going to be inverse sine of u plus c, where u was x over 3. Okay, so the antiderivative there is 4 times inverse sine of x over 3. I would encourage you, specifically with this section, since we're learning new functions, and if e to the x and natural log of x are still, if there's any hesitancy at all in those derivatives, go back and do from the book. If you go to WebAssign and you click on the ebook at the top, go and just do as many examples as you can. This is one place where just doing tons and tons of examples is just going to hammer this concept down. And I want these to be really immediate when we do these derivatives. Okay, so particularly with these inverse trig functions and the exponentials and logs, I just want you to, if I ask derivatives, I want you to be able to just rattle them off, tell me what they are without thinking about them too much. Okay, so just practice, practice, practice with these.